We're going to review. The nice thing about what we're doing today, which is just starting polynomials, is it ties together a few things that you learned in grade 9 and in grade 10. Like today we're going to touch on it a little bit, but over the course of the whole couple of units that we're spending on this, it ties together a few things that you've been learning about but had no idea why. Like the degree of a polynomial, you can see its definition up there. You learn about that in grade 9 and you learn how to do it, but you're like, you don't learn anything about who cares, why is that a thing, what's the definition, like we don't know anything about it, I don't think.
I just have a question about degree.
Sure.
If something is a square, does that have a degree? Right? Is it the degree of what it is squared? Does it have a degree of 2? If it's like 4?
Yes.
Okay.
No, 2. We'll get to that. Hold that thought. I thought you meant a square like the shape, and I'm like, yeah, kind of. Like a square shape is related to degree 2, but that's not what you meant. But okay. So anyway, and I was like, good insight. Great job, Lucy, but that's not what you meant. So we'll get to that. But it's neat because it ties some of these ideas together. But I'm going to tell you, there's 2 to 3 sort of big things you need to get out of today. One of them is notation, and you may not be awesome at it and fully get it today. That's okay. It might take a couple of days, but by the end of the day tomorrow or Friday, or definitely by our first quiz, you need to make sure you've got the notation down. So that's one thing you really need to make sure of. Is the new notation that we're learning. It's brand new. It's big in calculus. So especially if you're taking calculus, you need to learn it, but we use it a lot in this course as well. It's a big way that we describe characteristics of all kinds of functions. So you gotta get it. So just make sure you do. Again, spend the time, spend the effort to make sure that you understand this notation. Ask questions if you don't. Okay, but we're gonna cover it today. And then the 2 other things are what does the degree of a polynomial and what does the leading coefficient, in particular the sign of the leading coefficient, what do those 2 things tell us about the polynomial, the graph, and the new thing that we're learning around notation? That's what you need to get out of this. So keep that in the back of your mind as we do everything today and all the activities and demonstrations that we're doing today. Keep that in the back of your mind that that's what you're striving towards. What does the degree and the sign of the leading coefficient tell us about the graph? That's the big idea from today. So let's get to these definitions. A polynomial is an expression, this is kind of interesting, in one variable for us, but you may have heard, or you would if you explored the internet and that kind of thing, of multivariable calculus, a multivariate calculus, and there's like multivariable algebra as well, but thankfully it's a little bit harder. We kind of sort of touch a little bit on it in calculus, but not really. But in this course, it's all single variable. And you'd be like, but sir, everything we do has 2 variables because it says y equals, x squared or something like that. I see 2 variables. So isn't this multivariable? No, because this is, again, the point of functions, single variable functions. If I replace the y with the name f, I only have a single variable. F is not a variable. F is the name of the function, and it has 1 variable, which is x. So everything we do is single variable, which is good because it makes it a lot easier. So a polynomial for us involves 1 variable and coefficients, and only the operations of addition, subtraction, multiplication, and non-negative integer exponents. This is important because for the next 2 units, everything we do deals with polynomials. So you kind of need to know what a polynomial is, I think, before you can move forward. So we're going to look at some examples of things that are polynomials and are not briefly. Okay, so that's first definition. Second definition, the degree of a polynomial in 1 variable, which is good. Again, that it's a little bit easier because it's only in 1 variable, is the greatest exponent on the variable of any one of the terms of the polynomial. So in grade 9, you do this. You get questions like this, A, B, C. Does anybody know what the degree of that is? Nope, close. It's 3 because they're being multiplied, so I would add them together. A has a 1 on it, B has a 1 on it, C has a 1 on it, so I'd add them together and I get, and this is why it's confusing, because if it's A plus B plus C, then the degree is 1, because they're adding, you don't add the exponents, but when you're multiplying, you do. But in 1 variable math that we're doing, you don't have this. it would be x plus x plus x, or x times x times x, which is x cubed. So like that confusion from grade 9 is non-existent in our course. But make sure you don't make that grade 9 mistake and say that the degree is 3 when you're adding. That would be really bad. Okay? We'll look at an example of this in a minute. If the definition is not obvious, that's fine. It will be. It's pretty straightforward. And then the leading coefficient, this is really, really important that you understand what this is. You may not have heard it referred to as the leading coefficient before. And you do talk about it in grade 9. We call it the slope. So that's a pretty big idea in grade 9. And you do talk about it in grade 10, although not this way, because in grade 10 you'll really only have the one thing. But it's the A value. It's the thing that makes the parabola stretch or compress is the leading coefficient, but it's not called that probably, right? But it turns out for polynomials that the leading coefficient is really, really important and tells us a lot about what the graph is like. So it's really useful. And the leading coefficient is the coefficient of the term with the highest degree. And that's the one that dictates the degree of the entire function. Okay? This isn't super important, but just generally, a polynomial would be written like this. So this is what a polynomial will look like. It's degree n, so the highest exponent, the biggest exponent is n, and we usually write that one first. It's nice when you do, because if it can trick you if it's not written that way. So an, like that's a subscript because that's the coefficient of that term is just an, okay? Plus an minus 1, so the coefficient of the next term, n minus 1, so that exponent's smaller than n, right? Because I've taken away 1, plus dot, 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 and then a2x squared, a1 to the x, a1 times x, and then the constant. And just generally, we could write all polynomials kind of like that. They may or may not have all all terms, sorry. And we'll see an example of that in a minute. Let's get into some examples because that'll kind of bring things into light. So example 1. Determine whether each of the following is a polynomial. If it is, state its degree and leading coefficient. Now, I want you to take a risk here because we're just starting this, and reading a few definitions does not really usually help a lot in actually getting stuff done. Sometimes reading definitions after you've tried some questions can be helpful, but just reading one doesn't usually help. But what do you think for that first one? Is it a polynomial or not? Okay, thank you for throwing that out there. Yes, it is. So this is a polynomial. Yes. What's its degree? Very good. And what was the other question? What's the leading coefficient? So we call that A. We often use A as like a sort of short form for the leading coefficient. And what is the leading coefficient? 1, thank you. And so the fact that it's positive turns out is what's kind of what we're interested in, whether it's a 1 or a 2 or a 3. I mean, obviously matters, but for us it won't so much. And again, what I was talking about before is I could write this as f at x equals 1x squared plus 0x plus 1. So I could add in, we call these ghost terms. I could add in a 0 coefficient for the x term because it's missing, and you could think of all of them as having all terms, but some of them we don't write because the coefficient is 0, something like that, right? But sometimes we see polynomials that don't have every one of the terms, but the biggest exponent dictates the degree, and the coefficient of that term is the leading coefficient of the entire polynomial. Okay, that's the first start of the big idea of what we're doing here. Next one, polynomial or not. I know you're guessing, but I can imagine you have a gut feeling about whether this one is a polynomial or not. So what do you think? Is it a polynomial or not?
Yeah.
Why do you think it is?
Well, I think it is because it includes all of the things.
Okay, interesting. Are you shaking your head or thinking?
I
don't think it is.
You don't think it is. Why?
I don't know. You said something about the 1 being positive and it's negative for that.
Okay, interesting.
Isn't division just like multiplication?
That very good. Division is like multiplication.
I think it is. It's just like if there's like an inverse graph kind of, it's just on the denominator.
Okay, interesting. All good ideas. There is a polynomial in the denominator. I'll agree with you on that.
I don't think it is.
Why?
It says a polynomial needs a non-negative integer exponent. When you like think,
I don't see any non-negative integer exponents there. Do you see one, Max?
no,
Well, I don't see one,
I mean there's one.
but there is one. If I write this out like that, it has a negative, it's integer, but it's a negative exponent. So that's a very good explanation that Max gave as to why this is not a polynomial. This is a rational function, unit 5. So to be continued on that one. We're going to learn a lot about those later on, but not polynomials. So none of the functions we deal with should be looking like that. Make sense? Everybody okay with that? C, polynomial or not? People are hesitant to guess. They're like, I don't want to be wrong. The whole point is being wrong. That's how you learn. What do you think? I see some nodding, yes? You think it is? I agree. This is like your perfect example of a polynomial. Something x to the 4 plus something x to the 3 plus something x to the 2 plus something x plus the constant. That's what a polynomial is. This is what a polynomial should look like. It might be missing some terms. It might have all of them. So what's its degree? So this definitely is, and its degree, don't add them together. 4 plus 3 is 7, plus 2 is 9, plus 1 is 10. No, my gosh, no. It's easier than that. This should be degree 4, right? Just because of this 4. The biggest exponent on a variable is 4. I don't care about exponents on numbers. And what was the other question that we're supposed to, oh, the leading coefficient, right. A is 5. The coefficient of that term that gives the degree, which is 5 in this case, is the leading coefficient. And it's positive as well, which is what we mostly care about. What about this one? Anybody recognize this one? You spent one day looking at this relation in grade 10, at least if you took grade 10 at Galt. What shape is this? What is this? What do we? Huh? No. Nice idea though. You're on the right track. It's a circle. It looks like Pythagorean theorem, doesn't it? But it's a circle, and circles are not polynomials because circles are not even functions. So this is definitely not. And very quickly, we don't have a ton of time, but this is still interesting. If I wanted to, like, polynomials can always be written as y equals and can always be written in this form. So you could always ask, by the way, this is not the kind of question you're going to see on a test like, are the following polynomials or anything, but I think it's important for us to contrast what a polynomial is and what it isn't, like when we're starting out. So that's why we're doing this. It's not really the kind of thing we're going to be doing. If I brought the x squared over, and then I would have to take the square root of both sides, and I'd get plus or minus. And what is another way of writing a square root symbol? Y equals plus minus bracket 25 minus x squared bracket to the 1/2. Remember doing that kind of stuff? No? So rational exponents, should have done that in grade 11. And so it's not an integer exponent, so this is definitely not a polynomial when we see it written out like this, but needless to say, it doesn't look anything like it's supposed to, so it's not. You had a question, huh?
No, I just was going to ask if you could do what you just did.
Ah, there you go. What about this one? This one's a function. It says f at x. You're not supposed to say that unless it's a function.
No,
Yeah, in the exponent. The variable is in the exponent. So we know we should know what kind of this is an exponential, right? And we will talk about exponential functions when we do exponential functions and logarithmic functions later on in the course. So we will revisit that as well and learn lots about it, but that is not what this unit is about. Integer exponents. X isn't an integer. I mean, x could be an integer, but it could also be lots of other things, and it's a variable, so it's not an integer. And oh my gosh, what about this one? We know a lot about this one. I hope by this point we better know a lot about this one. Is that a polynomial? Oh my goodness, no. Trigonometric, obviously, not a polynomial. Trig, that's a whole different operation. We said addition, subtraction, multiplication. Not trigonometric things, right? So definitely not. Everybody good? Any questions about that? Okay, here we go. This is where we're starting. We're not going to fill in this whole table. We're only going to fill in the first 2 columns so that we can move on to bigger and better things. This is the notation that you need to learn. It's brand new, which means it takes some time to get used to. So it'll take a few days. And the only way you'll get used to it is by practicing and trying and asking and thinking about it and checking your answers and seeing if you're right or you're wrong and that kind of thing. But once you get it, it's not hard. It's actually really easy. But it's notation, right? It's kind of like spelling. Like you need to learn to spell words. It's not about making sense. It's just about learning how they're spelled. It's sort of similar to that. So it's called end behavior. And the end behavior of a function, and we do this in almost every unit that from here on out, okay? So it's a pretty big deal. End behavior of a function describes what the graph does as it goes off the page. There are two ways we use to describe it. Using quadrants, which is kind of a natural way of doing it. But usually on tests or quizzes, you will be required to do it the formal way. So we'll take a short look at both today. And you know, the quadrants one is pretty easy. The other one takes a bit more getting used to. And you've actually kind of seen this before when you did quadratics in grade 10 and you talked about whether a parabola opens up or down. But because parabolas only have those two options, there's no point in getting into more complicated stuff. So all you ever said was it opens up or it opens down. But we're going to have a new way of sort of describing that kind of behavior. Okay, but it's a similar idea as to a quadratic or parabola opening up or down. Okay, here we go. We're going to do linear and quadratic and skip the rest, but try to follow me. Now I'm going to color code things. You can't do that, so you can copy down either. Well, maybe you can. Oh, some of you are like, oh, yeah, sir, watch me. I'm going to pull out my pens. So you can do that, but you don't have to. You could just write down one example or the other. Trust me, over the next few days, we're going to do a lot of this, and you'll probably get it, so it's not a big deal. But if you want to look at my notes online, it might be helpful, because they'll be color-coded. So I'm going to do two equations here, y equals x plus 3, and y equals negative 2x. So what I notice is they have different leading coefficients. One of them's positive, one of them's negative. They're both degree 1, which we also call linear. So what would the x plus 3 graph look like? It's got a y-intercept of 3, and it's sloping that direction, right? That's a positive slope. And what would the other one look like? It would be sloping the other direction, and it would be a bit steeper, and it would go through the origin. Don't worry too much about those specifics, but that's what they would look like. Again, those lines more or less match the colors there, right? So here's what end behavior, here's the formal version. We always start by asking the question. So we start with x, because x is always our input, so we almost always start with x, right? That's kind of the way this all works. So we say, as x goes to positive infinity in this case, then what we do is we ask, what does y do? So watch. In this green graph, x going to positive infinity means as I go out to the right side of this graph. What is the green line doing? Yeah, it's going up to positive infinity. So in this case, as x goes to positive infinity, y also goes to positive infinity. But what about the other one? Because as x goes to positive infinity, what's y doing? It's going down, which is negative infinity. Because it's relative to x going to positive infinity. Yes, it's always up or down. Why will they'll? Yeah, but watch. What about as x goes to negative infinity? So that's the other direction that we're asking about now. As x goes to negative infinity, the green line is going to positive infinity or negative infinity. Which one? To negative infinity. So y goes to negative infinity. And for the purple line, as x goes to negative infinity, so again, as x is going this way, this line's going this way, and it's going up. So it's going to positive infinity. So this is, remember, this is just notation. If it looks confusing, it's actually not that bad. It's a strange notation because you've never seen it. A little hint of things not in this unit but down the road. In this unit, they'll always look like this. But not every graph goes to infinity. So it can go to other numbers. Okay? It can go to like asymptotes and stuff. Other kinds of functions do other things, but polynomial functions don't. So for now, this is good enough for us. It'll always go to positive infinity or negative infinity. But you have to figure out which one. So again, for quadrants, it's easier, but it's not the one that we prefer, so we don't use it that much. Looking at the green graph starts in quadrant 3 and goes up to quadrant 1. So that's exactly what we say. Quadrant 3 to quadrant, theta, where'd that come from? Quadrant 1. And the purple graph starts in quadrant 2 and goes to quadrant 4. So that one's a little bit easier, right? Like that one is like, yeah, I get that one. I still don't fully get the other end behavior. But what you need to understand is they're saying the same thing. This is as x goes to positive infinity, y goes to positive infinity, is saying the same thing as going up to quadrant 1. Means the same thing. Adam?
So if, for example, like the y equals x plus 3, does it matter that it goes to the second quadrant on say F?
No, not at all. Very good question, because end behavior, we don't care about what happens in the inside part of the graph. All we care about is when all that junk gets settled and the arms of the graph are going out pointing somewhere, where are they pointing? That's all we care about. Okay, here we go. Quadratic. Y equals x squared minus 7. Y equals negative x squared plus x. How about that? I'm not going to try to draw these accurately. The x squared minus 7 I can. Actually, I guess both I could, but. So this one's going to go something like this. And this one's going to go something like this. And then we ask the question. So we're talking about the green graph right now. And remember, what we're asking is, as x goes to positive infinity, so we're going out this way in the graph for green, what is that end arm? Where is it pointing? Where is it going? Positive infinity. It's going up. It's going up forever. It's never going to stop. So y goes to positive infinity. And let's do both the green ones now, because this is what's different. That was the same as linear, right? But what's different here is as x goes to negative infinity, what's y doing? Still going to positive infinity, right? Still going to positive infinity. As I'm going for the green one, as I'm going out to the left part of the graph, it's still pointing up. Okay, and for the purple, as x goes to positive infinity, y goes where? Negative infinity. And as x goes to negative infinity, y goes to still negative infinity. And you know a lot about parabolas, so you know very well that those are the only two options for a parabola. They're either both pointing up or they're both pointing down. Right? And what would the quadrants look like for this one? So for green, start in quadrant 2, end in quadrant 1. Remember, if you understand the quadrant stuff, but you're still not fully sure of the other notation, they're saying the same thing. They're just saying it in different ways. if like some people think they don't understand this, where really what they don't understand is the notation. That's what they don't understand. But you understand the idea that the ends of the graph are pointing off into infinity, right? Like people understand that. It's just how do we describe it?
You also say Q1 goes to Q2.
No, we usually go left to right. I'm sure that if you said that, people would figure out what you meant. But again, as a standard, we always kind of read left to right on the graph. I'm going to give you a little tip here, and forgive me because there's only a couple of times in my life when I dance, and it's always when I'm teaching. If you were with me in grade 10 and you learned how to factor complex trinomials, I dance when I factor complex trinomials. So that's one of the times I dance, and this is one of the other times that I will dance. So for polynomial functions, it's like disco dancing, by the way. Any disco fans in here? Okay, yeah, good. For polynomial functions, there's really only a couple of options, and this is what we're exploring over the next little bit. You guys are on the edges of your seat, I can tell. You're like, what is about to happen here? So what did linear look like? Like this. Or like this. What was quadratic? Like this. Or like this. And it turns out those are all of the possibilities. They're either going to point opposites like this, or they're both going to point up, or they're both going to point down. And we can figure, and it turns out that's really important, and we can figure that out just by looking at the degree and the sign of the leading coefficient. And so we're going to do a little activity here, and this is what we're going to do a little bit differently than we did last time because it didn't work very well. I'm going to demo stuff, and I just want you to watch, okay? So I'm going to show you a demo of something here. And the purpose for this is we're trying to determine what's always true for a polynomial. So I'm going to show you a bunch of different polynomials of different degrees, and you're going to notice some of the things are going to change characteristics of the polynomial. In other words, the graph is going to look different. But some of the things won't change, and that's what you're looking for. No matter what I do, I won't be able to change certain things for the graph. So here is, what kind of graph is that, by the way? Linear, and it's degree 1, right? And we know a lot about that. So if I drag this, it just moves it up and down. I'm changing that number right there, right? I'm changing like the y-intercept, okay? So I can move it up or down, not very interesting. And I can slant it by changing the slope, right? And changing this doesn't change the slope. So like think about end behavior, quadrant 3 to quadrant 1. And I can do that, right? So I would ask you this question. Could a linear graph ever have end behavior like a parabola? Both pointing up, both pointing down? No. So every linear graph, linear is not very interesting, right? There's not much to do, but we'll go like this, or like this, right? Okay. So if I make this quadratic, and again, we're kind of skipping over this because you've done lots of quadratics. You know that parabolas will always either both point up or both point down. There's no secret parabola that does something else, right? So and in grade 10 you talk about it opening up and opening down, and so they will always look one way or the other, right? And no matter what I do, like I can change this as much as I want, but it doesn't change the end behavior, and I can change this as much as I want, but it doesn't change the end behavior. Yes? That's not a parabola, and it's not a function, so it's not polynomial, but you can graph those things. In grade 11, you do the inverse of a function, and you graph parabolas on their sides, and then you restrict the domain and do all kinds of this silly nonsense that's just sort of exploring math stuff, yes. And we'll do a little bit of that in this course as well. But it's kind of like the square root function as well, right? But it only has half the graph. Yeah, okay, very good. Good questions. All right, here we go where we start to get some interesting stuff. So what happens when I do this? Take a look at that equation there, and I'll mix it up a little bit by just kind of dragging some of these things around. There we go. What's the degree? 3. What's the sign of the leading coefficient? It's 2 and it's positive. So I'm not going to change those things. I'm going to change the other things. You will watch what's changing and what isn't. And that's always just going to move it up or down. What? Okay, hold on. Now, remember the leading coefficient was positive 2? Now it's negative 2. What changed? What changes? What doesn't change? What is this graph? It's a degree 3 polynomial. And it's a better answer than I am. Yes?
So, like, the degree is positive, it still stays as in, like, going infinitely positive in, like, the first and third quadrant.
So notice, did any of those degree 3 functions look like this? Or like this? They all look like this and like this? Like the what? Like which function? Like the linear function, right? So degree 1 was always like this or like this. Degree 3 was always like this or like this. Always. And if, think about, hold on, some of you are getting there, I can tell already. Think about a linear with a negative slope would have the same end behavior. It'd be sloping this way, right? And if it was positive, it would have end behavior like that. Like that almost looks like a linear, except it's got a little squiggle in the middle, right? Okay, before there's any I can only imagine what people are about to say. Are you trying to draw a conclusion?
Yeah.
Okay, not yet. So let's up it to degree 4. Watch what happens when I change the b from 0 to some, let's go positive first. You can predict. If you have a rule that you're building, make a prediction based on your rule, then you get to see if it's right or wrong. Now watch what happens is, so I'm not going to change that. This is now a degree 4, right? Degree 4, we can see right there, x to the 4, and it's a positive 2, so positive leading coefficient, okay? And so watch as I change other things. And I can zoom out a little bit if we want to see what's happening there. Okay, and then I can change this, I can change this, I can move it up. Ooh, how many intercepts does it have? Ooh, now how many does it have? Now how many does it have? Now how many? Now how many? Those are interesting questions too. Okay, what about, let's see. Can I do anything different? Okay, that's maybe about as good as I can get making it different. What never changed? Okay, that was positive 2, negative. Now let me get these guys back so we can see the rest of the graph and see what's happening, because it's a little hard to tell. How many of you thought that's what was going to happen? You don't have to worry about why that's happening. That's not something we're worried about. All you're worried is about, you can see that the middle of the graph changes, but there's part of the graph that isn't changing. Hold on. So we're going to do this one more time. Let's change it. So that's a negative leading coefficient, by the way. Now we're going to change it to degree 5. And hopefully even more people have a prediction, okay, of what's going to happen here when I change it to degree 5. And I'll make it positive. Get it? Yep, so no matter what I do, I'm changing the insides of the graphs. Never changing the y-intercept, right? Because the y-intercept is right there. No matter what I do to the rest, it's always that constant. So it's always going through the y-intercept. But I can change everything else. And what's going to happen if I take the leading coefficient and making it negative? And I can get a lot of squiggles. The higher the degree, the more squiggles. That's a technical term, by the way. That's an official math term, squiggles, in the middle of the graph. Okay, so what's happening here? What are we noticing? What are we picking up on?
When it's odd, it behaves like linear, and if it's positive, if the coefficient is positive, then it's the same as a positive linear, and if it's negative,
Very good.
it's a negative linear.
Yeah.
If it's even,
Even degree.
a positive even degree acts as a normal parabola, and then a negative coefficient acts as a negative parabola.
Right. So this is a big idea of what you need to get out of today. Turns out this is really important. It tells us a lot about the polynomial we're looking at. So I can look at just the equation of a polynomial graph, any polynomial, degree 11. If I know it's degree 11, and I know it's positive 5 leading coefficient, I know it's going to go something like this, right? So odd and positive, odd and negative, even positive, even negative. Even degree, always both are, the end behavior are both up, both down. And odd, the end behavior are going different directions every single time. And the stuff that happens in the middle is like different. That's coming from somewhere else. And we'll look at that a little bit. And then we look at that more in calculus. But that's not the biggest part of all we're talking about today is the end behavior really, is what's going as we go out to the ends of the graph, where are things going? Any questions about any of that? What do you think?
How was the first person been able to graph that without a computer?
Really good question. How would they have?
I mean, it's not that.
Yeah,
You take the
if you got a graph piece of paper and it got negative 5 to the x to the 5, with 2 to the x to the 4, and then all that, you just be able to graph that.
So I'll tell you this. There's a form of the equation that's more familiar, better for graphing, just like vertex form of a parabola. There's nothing quite like that. But there's, so there are forms for graphing these things that are more friendly than standard form, which is awful for almost everything. And 2, 3, 4, 5, 6. And you can fairly simply algebraically test what's happening, because I could just put positive x values into any equation and see what the pattern is, and you'd see they'd get big, and they'd get big fast. Like, look, here's 1, and it's right around 0. Here's 3, and it's going to be like hundreds. And you could very quickly see, like, okay, this graph is like getting huge. So you would know the end behavior. And in fact, we do this kind of testing where we put in values and see what we get, and we're like, okay, so this is going whoop, way over like that. And then if I put in positive 5, I'd have some giant negative value. So you could maybe safely assume that you know what that's happening. So you could test these things algebraically, but yeah, it would have been hard to graph some of these things without computers. It is possible, though. Okay, let's see what we have here. Okay, so what we're going to do, sorry, I've got to erase some of this stuff because we're going to talk about this, is summarize what we found here so you have a copy of this in your notes, and anybody who's still maybe not quite sure, remember what I said, by the end of today, you want to have some understanding of what the degree of a polynomial function along with the sign of the leading coefficient tells us about the function. It tells us some things but not everything, right? And we're going to learn about a couple other little pieces of terminology, excuse me, that I haven't covered yet. And we're going to also ask questions like, how many X-intercepts could the graph have? This is interesting in lots of ways, and it's a question that sometimes comes up on assessments. So it's something you do want to spend some time thinking about. And you can develop your own rule. I'm not going to give you one, because memorizing a rule in that case to me is bad, and I would like you to spend some time thinking about it.
Does that include like rotating that makes any sense? Like, can you like rotate it to make sure all the like possible lines hit it?
Go ahead.
Here, I'll try to come back with.
Yeah, your question might get answered as we go through this, so we can probably talk about it again after. Okay, so We're talking about linear here. Linear is the word, another word we use for degree 1, and as we noticed, that's odd. So that tells us that the lines are either going to go this way, and that's for positive, or they're going to go this way, which is for negative, right? So all the ones down this column are positive, and all the ones down that column are negative. The maximum number of x-intercepts, can you visualize a linear graph with more than one x-intercept? I hope not. How would that work? It would have to like turn and come back down. Doesn't make any sense. By the way, this is the other terminology that we're talking about, is a turning point, and that'll make a bit more sense when we talk about quadratics, but you can see that a linear graph never turns. It's a straight line. Don't forget, these are all examples of polynomial graphs. Polynomials all look like these for the most part, right? Some variation on the idea of the graphs that we have here. Those other graphs that we looked at, exponential sign doesn't look anything like these, does it? Exponential doesn't. What does exponential look like? It looks like this, right? So it doesn't do the same thing. This end behavior is not going to positive infinity or negative infinity, is it? What's it going to? Zero, yeah. This one's going to 0. So other graphs do other things, but polynomials do the things we're talking about right now. That's what asymptotes are, yeah. So polynomials don't have asymptotes ever. They all share a pretty big set of characteristics, polynomial functions. Okay. So maximum number of turning points is 0. You can't turn a linear graph. You already know that. Could you have 0 x-intercepts? What's the minimum number of x-intercepts? It says 1. Could you have 0? What about a horizontal line, people might say? But a horizontal line would actually be like y equals 3. What's the degree of that function? Like, it's a straight line, so we think of it as linear, but it's degree 0. So it's not degree 1, so it's not the same. Right? That's not a hugely important idea for us, but it does make sense, and it is true. Okay, and so technically a degree 1 function, polynomial function, will have maximum 1 intercept, x-intercept, minimum 1 x-intercept. Okay, let's get to quadratics. The maximum number of x-intercepts is going to be 2. I can see it in this graph right here. By the way, some of the graphs on your sheet might look a little bit different from mine. That's kind of on purpose, so you can look at different examples of these graphs, because some people, their brains are very concrete. So they like the specific examples that they see and don't think of, well, what else could it look like? Like, both of these have 2 x-intercepts. So is that going to be true of every parabola? No. Can a parabola have 1 x-intercept? How? Okay, good. Yeah. Say again? Yes. Is on the x-axis. The vertex, or this is what we call a turning point. Okay, so I'm going to write this down because this is also terminology we use. A turning point, which for the parabola is the vertex, but other graphs have more than one turning point. So it's there and it's there. If the vertex or that turning point is on the x-axis, it has 1. Could it have 0? I hope this is an easy question. Yes. If it opens down and it's below the x-axis or whatever above and opens up, it will have 0 x-intercepts. So what's the minimum number of x-intercepts for a quadratic is 0. Yeah, beautiful. That's what I said. Like some of yours are different from mine, so that you see different kinds of graphs. Any other questions? We know a lot about quadratics, not very interesting. Oh, could a quadratic have more turning points or fewer turning points than 1? No, it's got to have 1. Every parabola has 1 turning point and only 1 turning point. But things change when we get into these examples. So cubic, we call these cubics, or degree 3, which is odd. And notice how this one has 2 turning points, and this one has no turning points. It's where the graph turns, literally. Remember when we talked about, thank you for asking this question, it's perfect. Perfect timing. Remember when we talked about increasing and decreasing functions? When a function is increasing or when a function is decreasing? We talked about that in the first unit a lot. So if it changes from increasing to decreasing, it has turned. Or if it changes from decreasing to increasing, it has turned. So take a look, you can watch. This graph here is decreasing, now it's increasing, now it's decreasing. Whereas this graph is increasing, still increasing. Even though it does a little flip or a little twist, or what did I call it, a squiggle? It does a little squiggle, it doesn't turn. So this one has 0 turning points, but this one has 2. Could a cubic, you don't have to answer these questions. You do need to answer these questions yourself at some point. Could a cubic have 1 turning point? A cubic has to be pointing up and pointing down. So like I would go like this. Okay, I'm going up, I've turned. Okay, when's it gonna, what am I gonna do here? What, I need it to be a cubic. I gotta turn again, I think, right? Don't you think? Yep.
I have a question.
Yep.
So, the number of like squiggles is equal to the degree minus 1,
Okay.
and the degree is how many potential.
Okay, so Lucas is trying to build a rule that would work to memorize some of the answers, at least, to these ideas. And I want to let everybody,
Right there. Oh.
kind of, yeah.
Okay.
No, but it doesn't say what you're saying. The maximum number of x-intercepts is equal to the degree. Yes, right. And you'll notice that, but I want people to also kind of think about that and develop that on their own. And then the maximum number of turning points, you're right, there's like rules that you can build for that. Yes, very good. Well, maybe we'll bring those up another time, but I'm going to let people continue to think about it. What are the possible x-intercepts for this? So again, we said you could have 0 turning points for cubic or 2, but not 1. What about x-intercepts? You could have a max of 3. We see an example here, or you have one that's got 3, right? It goes like this, like it crosses, like it clearly crosses 3 times. So you could have 3, that's the max. Can you have 2? And this is like a question, again, even if it's rhetorical, we don't need to answer right now, but for yourself, answer it. Could you have 2? What would that look like? What if on a quiz or a test I said, draw a random example of a cubic function with 2 x-intercepts if you can? And you would have to understand what that looks like and what that means. Can you have 1? Yes, we've got an example of that right there. Yes. Could you have 0? If you're looking like this, how could you have 0? Right? So interesting. Okay, and then quartic. And I drew in a few other examples of some quartic. So quartic is degree 5, or degree 4, sorry. Maximum number of x-intercepts is 4. And do you have an example of that on your page? The 4 one? Is that true? Does yours look a little bit different from mine? Oh. So what would 4 look like? It'd be like 1, 2, 3, 4, right? It would just clearly cross 4 times. This is an example of 3 turning points, sorry. So 1, 2, 3 turning points. 1, 2, 3 turning points. This one only has 1 turning point. So there's some options here. Could you have 2 turning points? 1, 2. Now what do I do? Yes?
So could you have anything from 0 to 4 x-intercepts?
How would you have 0 x-intercepts? Yeah, like those are 2 really terrible examples of possible graphs, right, that are below and opening downwards. So you could have 0 x-intercepts. Could you have 1? Could you have 2? Could you have 3? Could you have 4? And if you haven't quite figured it out yet, the possibilities for x-intercepts are very different from the possibilities for turning points. X-intercepts 0 to 4, but turning points, it doesn't work out that way. Rather. Big time, yeah. Right?
Yeah.
And it also depends on the degree. Because every time we go up a degree, we're adding more turning points. But exactly how many turning points has to do with whether it's even or odd. Yep.
Wait, so the first one, that's one turning point?
This one only has one turning point. That's like a twist, we call it. It's not really called a squiggle, but we call it a cubic twist or a twist. And that has a twist in it and one turning point. Yep.
So the number of vertices is equal to the number of turning points?
Yes. We don't call them vertices. Some people might. We often don't call them like a vertex. We say a parabola has a vertex. But you're right, that if I cover up the rest of the graph, that looks like a parabola with a vertex. And that's what a turning point is, yeah. Because before that, it's decreasing. And then after that point, it's increasing. So it turns, literally turns. That's why we call it that. Any other questions?